Tonight, we're going to tell you about the moment humanity finally saw a place it had never seen before. Not a distant planet, not a faraway galaxy, something far closer and far more important. The top of our own star. For the entire history of our species, through every civilization, every telescope, every space mission, no human being and no machine had ever looked down upon the pole of the sun. It was the single greatest blank spot on the map of our own solar system, the one region of our nearest star that had remained, quite literally, unseen. And here is the strange part. Even though we had never seen the sun's poles, we thought we knew what was there. We had drawn a map, based on everything we understood about the sun, based on our models and our theories and our glimpses from the side. We had filled in that blank spot with our best picture of what the pole of the sun must look like. A tidy, orderly place. A clean magnetic pole, much like the poles of a simple bar magnet or the poles of the Earth. That was the map we carried in our textbooks and our minds. That was the picture of the top of the sun that everyone assumed was correct. Then, in the spring of 2025, a spacecraft did something no spacecraft had ever done. It climbed up out of the flat plane where all the planets orbit, rose high above the level of the sun's equator, and turned its cameras downward to photograph the sun's pole for the very first time in history. And when the images came back, when we finally saw the top of our own star with our own eyes, we discovered something humbling. The map was wrong. What was actually there was not the tidy, orderly pole we had drawn. It was something messier, stranger, and far more chaotic than the simple picture we had imagined. And that chaos, it turns out, is tied to the single thing about the sun that we most desperately want to predict and still cannot. By the end of tonight, you're going to understand why we had never seen the sun's poles, what map we had drawn in their place, and what a spacecraft actually found when it finally climbed high enough to look down on the top of the sun. You're going to understand why the map was wrong, what the real pole looks like, and why this discovery matters for every single one of us here on Earth. This is the story of the last unseen place in our corner of the cosmos, and the moment we finally saw it for what it truly is. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. To understand why this discovery matters so much, you first have to appreciate something genuinely astonishing. In all the time humans have been studying the sun with all our incredible instruments and spacecraft, there was one part of our own star that we had simply never seen. Not seen poorly, not seen unclearly, never seen at all. The poles of the sun were the last great blank spot, an unexplored frontier hiding in plain sight at the top and bottom of the brightest object in our sky. Think about how strange that is. We have studied the sun in extraordinary detail. We have mapped its surface, tracked its spots, measured its eruptions, and probed its interior using clever techniques that read the vibrations rippling through it. We have watched the sun continuously, around the clock, for decades with a whole fleet of spacecraft and observatories. We have flown a probe right through the sun's outer atmosphere, closer than any object we have ever sent. By any reasonable measure, the sun is the most thoroughly studied star in the universe, examined more closely than any other. And yet, despite all of this, there remained one region of the sun that had eluded us completely: its poles. The very top and the very bottom of our star had never once been photographed, never once been seen from above, never once been directly observed. They were, in the words of one scientist who studies the sun, literally terra incognita, unknown territory, a blank space on the map of our own star. Why had we never seen the poles? The answer, as we will explore, comes down to a kind of trap, a fundamental limitation in where we are able to look at the sun from. And that limitation meant that for all our study of the sun, its poles remained hidden, glimpsed only from the side, distorted and foreshortened, never seen properly from above. It is a bit like knowing a mountain intimately from every angle at its base, but never once being able to see its summit. You could study the mountain your whole life, learn every detail of its slopes, and still have no real idea what the very top looked like, because you could never get above it. That was our situation with the sun. We knew it in extraordinary detail, everywhere except the one place we could never rise high enough to see. And this blank spot was not just a minor gap in our knowledge. It was, in a very real sense, one of the most important regions of the sun, a place that holds the key to some of the deepest mysteries about how our star works. The poles of the sun are intimately tied to the great rhythm of solar activity, to the cycle that governs the sun's storms and eruptions, the cycle whose effects reach all the way to the Earth. So the fact that we had never seen the poles was not just a curiosity. It was a genuine hole at the heart of our understanding of the sun. To fill that hole, to finally see the last unseen place, would require a spacecraft unlike any that had come before, one designed to break free of the very trap that had kept the poles hidden. But before we get to how we finally saw the poles, we have to understand exactly why they had remained invisible for so long. And that story begins with the blank spot on the map, and with the strange geometry that had kept it blank. Let's begin by appreciating just how complete our map of the sun actually was, everywhere except the poles. Because to understand the significance of that blank spot, you have to understand how much we had already filled in around it. We knew the sun in extraordinary detail, and that only makes the empty space at its poles more remarkable. Consider everything we had already mapped. We had watched the sun's surface continuously for decades, tracking the dark sunspots as they formed and drifted and faded. We had recorded countless solar flares, those enormous explosions on the sun's surface, capturing them in exquisite detail across many different wavelengths of light. We had observed the sun's outer atmosphere, its shimmering corona, and watched it hurl vast clouds of material out into space. We had even developed ingenious ways to peer inside the sun, reading the subtle vibrations that ripple across its surface to deduce what was happening in its hidden depths, a technique that let us map the sun's interior structure and its internal flows. We had spacecraft stationed at various points, watching the sun from different angles, monitoring its activity every hour of every day. Our knowledge of the sun was, in most respects, breathtakingly detailed and complete. We had built a rich, intricate map of our star, covering its surface, its atmosphere, and even its interior. But there was a catch, and it was a big one. All of this detailed observation shared a hidden limitation. Almost everything we knew about the sun came from viewing it from essentially the same vantage point, from more or less the same angle. And from that angle, there were two regions we could never see properly. The very top of the sun, its north pole, and the very bottom, its south pole. These polar regions were always at the edge of our view, seen edge on, at a steep and distorting angle if they could be seen at all. Imagine trying to photograph the top of someone's head when you can only ever look at them from eye level straight on. You would see their face perfectly, but the top of their head would be just a sliver at the upper edge of your view, foreshortened and unclear. That was exactly our problem with the sun's poles. We could see the sun's equatorial regions beautifully, straight on. But the poles were always at the extreme edge, glimpsed at a hopeless angle, never seen from directly above. So on our otherwise detailed map of the sun, the poles remained a blank spot, or at best a badly distorted smear. We had never obtained a clear, direct, overhead view of either pole, and this was not for lack of trying or lack of interest. Scientists desperately wanted to see the poles because they knew how important those regions were. The problem was not our instruments, which were superb. The problem was where we were forced to look from. We were trapped at an angle that made the poles impossible to see properly. And this trap, this fundamental limitation on our viewpoint, is the key to understanding why the poles had remained hidden for so long. It is a trap created by the very structure of our solar system, by the flat plane in which the Earth and all our spacecraft are confined. To understand why we had never seen the poles, we have to understand this plane and the cage it creates around our view of the sun. We have established that we could never see the sun's poles properly, always glimpsing them at a hopeless, edge-on angle. But why? Why were we stuck viewing the sun from a vantage point that hid its poles? The answer lies in a fundamental feature of our solar system, a kind of invisible cage that confines nearly everything we have ever sent to space, and that had kept the sun's poles hidden for the entire history of astronomy. Here is the crucial fact. Our solar system is remarkably flat. The Earth orbits the sun, and so do all the other planets, and almost all of them orbit in nearly the same flat plane, like marbles rolling around on a tabletop. This flat plane, the plane in which the Earth and the other planets orbit the sun, is called the ecliptic. And it is not a minor detail. It is the dominant geometry of our entire solar system. The planets do not orbit the sun at wildly different angles, tumbling above and below in all directions. They orbit, more or less, in the same flat sheet, circling the sun around its middle, around its equator. The whole solar system is shaped like a flat disk, with the sun at the center and the planets orbiting around its equatorial belt. Now think about what this means for our view of the sun. Because the Earth orbits in this flat plane around the sun's equator, we always view the sun from the side, from the level of its equator. We are, in effect, permanently positioned around the sun's waist, looking at it edge-on. And from that position, around the equator, the sun's poles are always at the extreme top and bottom of our view, seen at a grazing, distorting angle, never from above. It is exactly like being confined to walking in a circle around a globe at the level of its equator. No matter where you walk in that circle, you can never see the top of the globe, the North Pole, because you are always looking at it from the side. To see the top, you would have to rise up, to climb above the level of the equator and look down. But confined to the equatorial circle, that top always remains hidden from a proper view. And here is the trap. Nearly everything humanity has ever launched into space orbits within or near this same flat plane, the ecliptic. Our spacecraft, launched from the Earth, tend to stay in the plane the Earth already orbits in, because it takes an enormous amount of energy to climb out of that plane. So virtually all of our solar observatories, all our spacecraft that watch the sun, have been confined to the same flat plane, viewing the sun from around its equator, just as the Earth does. This is the cage of the ecliptic. It is a fundamental limitation imposed by the flat structure of our solar system and by the difficulty of escaping that flatness. And it meant that, for the entire history of space exploration, we had been stuck viewing the sun from its equator, unable to rise up and look down on its poles. The poles remained hidden not because we lacked the instruments to see them, but because we could never get to a vantage point above them. Breaking free of this cage, climbing up out of the flat plane of the solar system, would turn out to be one of the great challenges of solar exploration. But before we see how that challenge was met, we need to understand what we thought was hiding at the poles, the map we had drawn of a place we had never seen. For all the centuries we could never see the sun's poles. We did not simply leave them as a total blank in our minds. Human beings are not comfortable with blank spaces on maps. We fill them in with our best guesses, our models, our extrapolations. And so, over time, we built up a picture of what the sun's poles must be like, a map drawn not from direct observation, but from theory and inference. This was the map we carried, the picture of the poles that most people assumed was correct. And it is worth understanding exactly what that map showed, because it is what would later turn out to be wrong. The picture we had was shaped, in large part, by an appealing simplicity. We know that the sun has a magnetic field, and the simplest, most familiar kind of magnetic field is the kind produced by an ordinary bar magnet, the kind you might stick on a refrigerator. A bar magnet has a clean, orderly magnetic field, with a distinct north pole at one end and a distinct south pole at the other. The magnetic field flows neatly from one pole to the other, tidy and symmetrical. And for much of the time, the sun's overall magnetic field does resemble this simple bar magnet arrangement, with a north magnetic pole and a south magnetic pole, and a clean field flowing between them. So it was natural to imagine that the sun's poles, the actual polar regions at the top and bottom of the sun, would be clean, orderly magnetic poles, much like the ends of a bar magnet. A single, well-defined magnetic polarity at each pole. North at the top, south at the bottom, or the reverse, tidy and distinct. This was the map we drew of the sun's poles, a place of magnetic order and simplicity. We pictured the top of the sun as a clean magnetic pole, with the magnetic field emerging or entering in an orderly way, a well-behaved region anchoring one end of the sun's overall magnetic field. It was a reasonable picture, based on sound reasoning about how magnets work and about the sun's large-scale field, and it fit with the tidy diagrams in textbooks, the simple illustrations of the sun as a great magnet with clean poles. This was the mental image that scientists and students alike carried, the assumed reality of the sun's poles, filled in on the map even though no one had ever actually seen them. The poles were imagined as orderly, simple, clean. But here is the crucial thing to understand about this map. It was a map drawn in the absence of direct observation. It was an extrapolation, a best guess, a picture assembled from theory and from our glimpses of the sun from the side. No one had ever actually verified it by looking down on a pole and seeing what was really there. And whenever you draw a map of a place you have never seen, you run a risk. The risk that reality will turn out to be different from your assumptions, that the actual territory will not match the map you imagined. The sun's poles were the ultimate example of this. We had a clean, tidy picture of them, but it was untested, unverified, built on inference rather than observation. And as we would eventually discover, when we finally rose up and looked down on the pole for the first time, the reality was considerably messier than the map. But before we get to that revelation, we need to understand why this blank spot mattered so much in the first place. Because the poles of the sun are not just any region. They may hold the key to predicting the sun's behavior, and that makes them some of the most important real estate in the entire solar system. It would be easy to think of the sun's poles as just another region to check off, a curiosity to satisfy our completeness. But the poles are far more important than that. In fact, the poles of the sun may hold the key to one of the greatest practical mysteries about our star, the mystery of predicting its behavior. This is why the blank spot on our map was not just an academic gap, but a genuine hole at the heart of solar science, a missing piece we desperately needed. To understand why, you have to understand the great rhythm of the sun. The sun is not constant in its activity. It goes through a cycle, roughly every 11 years, in which its activity rises to a peak and then falls to a lull, over and over. During the peak of this cycle, the sun is covered in sunspots and erupts frequently with powerful flares and vast clouds of charged particles. During the lull, the sun grows quiet, its surface calm, its eruptions rare. This 11-year cycle of solar activity is one of the most important patterns in our entire solar system, because the sun's eruptions, when they are aimed at the Earth, can disrupt our technology, damage our satellites, threaten our power grids, and endanger astronauts. The rise and fall of solar activity directly affects the space, whether that reaches the Earth. And so, predicting this cycle, knowing when the sun will be stormy and when it will be calm, is enormously valuable, both scientifically and practically. And here is where the poles come in. The great cycle of solar activity is driven by the sun's magnetic field, by the way that field builds up, tangles, and reverses over the course of the cycle. And the polar regions of the sun play a central role in this magnetic cycle. The magnetic field at the poles is thought to be a kind of seed for the next cycle of activity, a key ingredient that helps determine how strong the coming cycle will be. In fact, the strength of the magnetic field at the sun's poles during the quiet part of the cycle is one of the best predictors we have for the strength of the next cycle of solar activity. The poles, in other words, hold vital clues about the sun's future behavior, about how stormy the coming years will be. If you want to predict the sun, you need to understand the poles. So now you can see the problem. The poles of the sun, this region that holds the key to predicting solar activity, were precisely the region we had never been able to see properly. We wanted to forecast the sun's behavior, to know in advance how strong the next cycle of storms would be, and the very information we needed was locked away at the poles, hidden by the cage of the ecliptic. We were trying to predict the sun while blind to one of its most important regions. This is why the blank spot mattered so much. It was not just an unexplored curiosity. It was a missing piece at the very heart of our ability to understand and predict our own star. Filling that blank spot, finally seeing the poles, could transform our understanding of the solar cycle and our ability to forecast the space, whether that affects us all. And that is exactly why scientists were so determined to find a way to break free of the ecliptic and rise up to see the poles at last. The question was how. How do you climb out of the flat plane of the solar system when everything we launch is trapped within it? The answer was a spacecraft designed to do the seemingly impossible. If the poles of the sun had remained hidden, because everything we launch is trapped in the flat plane of the solar system, then seeing the poles would require something extraordinary. A spacecraft specifically designed to escape that flat plane, to climb up above the level of the sun's equator and look down on the poles from above. This was the mission that would finally fill in the blank spot on our map, a spacecraft built, quite literally, to break free of the cage that had confined all our previous views of the sun. This spacecraft was a mission led by the European Space Agency, with contributions from the American Space Agency, and it launched at the start of this decade, beginning its long journey to the sun. From the outset, this mission had an ambitious and unprecedented goal, not just to study the sun up close, but to do something no mission had ever done, to climb out of the ecliptic plane and obtain the first direct views of the sun's poles. This was the mission's defining ambition, the thing that set it apart from every solar mission that had come before. Other spacecraft had watched the sun from within the flat plane, from around its equator. This one was designed to leave that plane behind, to tilt its orbit and rise up, gradually climbing to a vantage point from which it could finally look down on the poles of the sun. It was, in essence, a spacecraft built to see what no one had ever seen. But breaking free of the ecliptic plane is extraordinarily difficult. Remember, the reason all our spacecraft stay in that plane is that climbing out of it requires an immense amount of energy. A spacecraft launched from the Earth naturally moves within the plane the Earth orbits in, and to tilt that orbit, to lift it up out of the flat plane and angle it above the Sun's equator, demands a tremendous change in the spacecraft's motion. You cannot simply fire a rocket and climb out of the plane directly, at least not with the amount of fuel a spacecraft can carry. The energy required is simply too great, so the mission faced a fundamental challenge. How to climb out of the ecliptic plane, to tilt its orbit high enough to see the poles, without needing an impossible amount of fuel. Solving this challenge required a clever and patient strategy, one that would use the gravity of a planet itself to gradually lift the spacecraft's orbit, little by little, over a period of years. This is the mission that would finally give us our first view of the Sun's poles, the spacecraft designed to break the plane and see the last unseen place. Its journey would be long, its climb gradual, and its strategy ingenious. And when it finally reached a high enough vantage point, it would turn its instruments toward the pole of the Sun and capture images that no human had ever seen, testing our old map of the poles against reality for the very first time. But to appreciate how it got there, we need to understand the clever trick it used to climb out of the flat plane, a trick that turned the gravity of a neighboring planet into a kind of staircase, lifting the spacecraft higher and higher above the level of the Sun's equator. It was a stairway, as one scientist put it, to the heavens. How do you climb out of the flat plane of the solar system when you cannot carry nearly enough fuel to do it directly? The mission that would finally see the Sun's poles solved this problem with one of the most elegant techniques in all of spaceflight, a method that borrows energy from the gravity of a planet to reshape a spacecraft's orbit. Using this technique, again and again, the spacecraft would slowly climb a kind of staircase, rising higher above the Sun's equator with each step, until it reached a vantage point from which the poles came into view. The technique is called a gravity assist, and it is a remarkable piece of cosmic strategy. The idea is that when a spacecraft flies close to a planet, it can use the planet's gravity to change its own path and speed. By carefully choosing the angle and timing of the flyby, mission planners can use the encounter to bend the spacecraft's orbit in a desired direction, effectively stealing a tiny bit of the planet's motion to reshape the spacecraft's trajectory. This lets a spacecraft change its orbit dramatically without using much fuel at all, relying instead on the gravity of the planet to do the work. Gravity assists have been used to send spacecraft all across the solar system, slinging them toward distant destinations they could never reach on fuel alone. And for the mission to see the Sun's poles, gravity assists would be used for a special purpose, to gradually tilt the spacecraft's orbit up out of the flat plane of the solar system. The planet that would provide these gravity assists was the Sun's neighbor, the second planet from the Sun, the world that orbits between the Earth and the Sun. Again and again, the spacecraft would swing by this planet, and each time it would use the planet's gravity to tilt its orbit a little further out of the ecliptic plane, lifting it a bit higher above the level of the Sun's equator. It was a slow, patient process, requiring many flybys over a period of years. With each pass by the planet, the spacecraft's orbit would climb a little higher, angling further above the Sun's equator, step by step, like ascending a staircase one stair at a time. One scientist involved in the mission described it beautifully, calling it the spacecraft's stairway to heaven, a gradual climb up out of the flat plane, using the gravity of a planet as the steps. Each flyby was another step upward, another increment of tilt, bringing the spacecraft closer to a view of the poles. This patient, ingenious strategy was the key to breaking free of the cage of the ecliptic. There was no shortcut, no single dramatic maneuver. Instead, there was this slow, methodical climb, flyby after flyby, each one lifting the spacecraft a little higher above the sun's equator. And as the spacecraft climbed this stairway, its view of the sun's poles gradually improved. From the flat plane, the poles had been invisible, seen only at a hopeless edge on angle. But as the spacecraft rose higher and higher above the equator, it began to be able to look down on the poles, to see them from above for the first time. The climb would continue for years, and it is still continuing today, with the spacecraft set to rise even higher in the years to come. But it had already climbed high enough by the spring of 2025 to capture the first real views of the pole. And to capture those views, it carried a set of remarkable instruments, each designed to reveal a different aspect of the mysterious polar region. These were the eyes we sent to see the last unseen place. When the spacecraft finally climbed high enough to look down on the sun's pole, it would need the right instruments to make sense of what it saw. Because the pole of the sun is not a simple thing to observe. There is the visible surface, there is the magnetic field, there is the churning atmosphere above, and there are the flows of hot, charged gas moving through it all. To capture this complex region properly, the spacecraft carried a suite of remarkable instruments, each one a different kind of eye, designed to reveal a different aspect of the pole. Together, they would give us our first true picture of the last unseen place. The most important instrument for our story was one designed to map the sun's magnetic field. This instrument could measure the magnetic field across the surface of the sun, revealing its strength and its direction, mapping out where the magnetic field pointed one way and where it pointed the other. This was the eye that would test our old map of the poles, because our old map was fundamentally a map of the magnetic field, a picture of a clean, orderly magnetic pole. This magnetic mapping instrument would look down on the pole and measure the actual magnetic field there, showing us, for the first time, whether the real pole matched our tidy assumptions or not. It was, in a sense, the truth teller of the mission, the instrument that would reveal whether the map was right or wrong. But the magnetic field was not the only thing worth seeing. A second instrument was designed to image the sun in ultraviolet light, capturing the sun's outer atmosphere, the hot layers above the visible surface. This ultraviolet eye would reveal the structure of the sun's atmosphere over the pole, showing the loops and features traced out by the hot gas, and revealing the imprints of the magnetic network on the layers above the surface. And a third instrument was designed to analyze the light coming from charged gas at different temperatures in the sun's atmosphere, allowing scientists to measure how that hot gas was moving, to track the flows of material over the pole. This instrument could reveal the velocities of the gas, showing how material was flowing across and around the polar region, uncovering the hidden currents of the sun's atmosphere at the pole. Each instrument, then, offered a different window. One mapped the magnetic field, one imaged the atmosphere, and one tracked the flows of hot gas. Together, these instruments formed a powerful set of eyes, capable of revealing the pole of the sun in unprecedented detail, across multiple aspects at once. They could show us the magnetic field, the atmosphere, and the flows, building up a rich, multi-layered picture of a region no one had ever seen. And crucially, they could test our old assumptions, comparing the real pole against the map we had drawn. When the spacecraft turned these instruments toward the pole in the spring of 2025, it would be the first time in history that such a complete set of eyes had ever been trained on the top of the sun. But before we witness what those eyes saw, there is a fascinating twist to the story, a piece of history that many people do not know. Because while this mission would be the first to photograph the sun's poles, it was not, in fact, the first spacecraft to ever travel over them. Decades earlier, another spacecraft had flown over the sun's poles, but it had done so completely blind. Here is a twist in our story that surprises most people. The mission that captured the first images of the sun's poles in 2025 was not actually the first spacecraft to travel over those poles. Decades earlier, another spacecraft had already flown high above the sun's polar regions, breaking free of the ecliptic plane in its own remarkable way. But there was a crucial difference. That earlier spacecraft could not see. It flew over the poles blind, feeling its way through the polar environment without ever capturing a single image. It was, in a sense, a ghost that went before, a pioneer that reached the poles but could never show us what they looked like. This earlier mission was a joint venture between the American and European space agencies, launched back in 1990, decades before our modern polar mission. And it accomplished something extraordinary. It became the first spacecraft ever to fly over the poles of the sun, climbing out of the ecliptic plane to pass high above the sun's polar regions. It achieved this using the gravity of the largest planet in the solar system, swinging by that giant world, and using its immense gravity to fling itself up and out of the flat plane, onto an orbit that carried it over the sun's poles. It was a triumph of spaceflight, the first mission to escape the cage of the ecliptic and travel over the polar regions of the sun, and it operated for many years, passing over the poles multiple times and gathering valuable data about the polar environment. But here is the crucial limitation. This pioneering spacecraft carried instruments that measured the environment immediately around it, sensing the magnetic field, the charged particles, and the flow of material at its location as it passed over the poles. What it did not carry was any camera or imaging instrument capable of taking a picture of the sun's poles. It could feel the polar environment, measuring the conditions in the space it flew through, but it could not see the pole, could not photograph it, could not show us what the polar surface or atmosphere actually looked like. So while this spacecraft flew over the sun's poles and gathered important measurements of the space around them, it never captured an image of the poles themselves. It sensed them without seeing them, sampling the polar environment while leaving the visual appearance of the poles as much a mystery as ever. The blank spot on our map remained blank, because this pioneer, for all its achievement, was effectively blind to the visual reality of the poles. This is why our modern mission's achievement was still a genuine first, even though a spacecraft had flown over the poles before. Because there is a profound difference between flying over a place blind, measuring the conditions around you, and actually seeing that place, capturing its image, looking down upon it with true eyes. The earlier mission had felt the poles but never seen them. Our modern mission would be the first to actually image them, to capture pictures of the pole and reveal its visual reality for the first time in history. The ghost that went before had opened the door, proving it was possible to reach the poles, but it left the poles themselves unseen. It would take a new mission, with true eyes, to finally look down and see what was really there. And in the spring of 2025, that mission climbed high enough to do exactly that, turning its cameras toward a pole that no eye had ever beheld, about to test our ancient assumptions against reality at last. By the spring of 2025, after years of patiently climbing its stairway out of the ecliptic plane, the spacecraft had finally reached a vantage point high enough to look down on the sun's south pole. It had tilted its orbit far enough above the level of the sun's equator that, for the first time, the pole came into a view that was no longer hopelessly edge-on. The moment that scientists had waited for, across the entire history of solar astronomy, had arrived. The spacecraft was about to capture the first real images of the sun's pole, and the mood among the scientists involved was one of genuine uncertainty and anticipation, because they truly did not know what they were about to see. One of the scientists who led the key instrument on the mission captured this feeling perfectly. He said that they did not know what exactly to expect from these first observations, because the sun's poles were literally terra incognita, unknown territory. Think about what a remarkable admission that is, coming from the very people who study the sun for a living. Even the world's leading solar scientists did not know, for certain, what the pole of the sun would look like when they finally saw it. They had their models, their theories, their old map drawn from inference, but they had never actually seen the pole, and so they could not be sure whether reality would match their expectations or defy them. There was a real sense of stepping into the unknown, of finally lifting the veil on a region that had remained hidden for the entire history of astronomy. This was genuine exploration, in the truest sense, a first look at a place no one had ever seen. This uncertainty is worth dwelling on because it captures the essence of what made this moment so special. So much of modern science involves confirming things we already largely understand, filling in details, refining measurements. But this was different. This was a first glimpse of an unexplored frontier, a moment when scientists genuinely did not know what they would find. Would the pole match the tidy, orderly map they had drawn? Or would it reveal something unexpected, something that would force them to revise their understanding? No one could say for certain. The pole was terra incognita, and turning the spacecraft's instruments toward it was a leap into the unknown, an act of true discovery. In an age when it can feel like everything has already been seen and mapped, here was a genuine blank spot on the map, about to be filled in for the very first time. And so, in the middle of March 2025, the spacecraft turned its instruments toward the sun's south pole and began to capture the first images ever taken of that region. Its magnetic mapping instrument measured the magnetic field at the pole. Its ultraviolet eye imaged the atmosphere above the pole. Its third instrument tracked the flows of hot gas across the polar region. The data was recorded and began its long journey back to the Earth, carrying with it the first true view of the last unseen place. Scientists waited to see what their instruments had captured, waited to finally lay eyes on the pole of the sun. And when the images came through, when the pole of the sun was revealed at last, what they saw would confirm that this was indeed uncharted territory. Because the reality of the pole, as we will now see, did not match the tidy map they had carried. The first true image of the pole was about to overturn the picture we had drawn. And then, at last, it happened. The images came back, and for the first time in the history of the human species, we saw the pole of the sun, not glimpsed at a hopeless angle from the side, not imagined or inferred or extrapolated, actually seen directly from above, captured by the eyes of a spacecraft that had climbed high enough to look down on the top of our star. It was a genuinely historic moment, the filling in of the last great blank spot on the map of our solar system, the first true image of a place no one had ever beheld. Let the significance of this sink in. For the entire history of astronomy, from the first people who ever gazed at the sun, through every great astronomer, every telescope, every spacecraft, no one had ever seen the pole of the sun. It had remained hidden, glimpsed only edge on, foreshortened and unclear, a region we could infer but never truly observe. And now, in a single moment that changed forever, the images from the spacecraft revealed the sun's south pole in real detail, seen from above, showing the magnetic field, the atmosphere, and the flows of the polar region as they actually were. It was the first time human beings had ever laid eyes on this part of our own star. A frontier that had remained unexplored for all of human history was, at last, an unexplored frontier no more. We had finally seen the pole of the sun. There is something profound about moments like this, moments when we see something for the very first time. They are increasingly rare in our thoroughly explored world. We have mapped nearly every corner of the Earth, photographed the planets, peered into distant galaxies. And yet here was a genuine first, a true act of discovery, the unveiling of a place that had been hidden in plain sight at the top of the brightest object in our sky. The scientists who saw these first images were witnessing something no human had ever witnessed, gazing upon the pole of the sun with true eyes for the first time. It was a moment to rank among the great firsts of exploration, the first views of a new and unknown territory, captured at last after a journey of years and a wait of centuries. But the true drama of this moment was not just that we had seen the pole. It was what the pole revealed. Because when scientists examined these first images, when they looked closely at the magnetic field the spacecraft had measured at the sun's south pole, they found something that did not match their expectations. The tidy, orderly map they had drawn, the picture of a clean magnetic pole like the end of a bar magnet, was not what the images showed. Instead, the real pole revealed something messier, more chaotic, more surprising. The first true image of the pole was also the moment we discovered that our old map had been wrong. And to understand exactly how it was wrong, we need to look closely at what the spacecraft's magnetic instrument actually found at the sun's south pole, because it was not a clean magnetic pole at all. It was a mess. Here it is, the heart of our story, the moment the old map met reality and was found wanting. When scientists examined the magnetic field that the spacecraft had measured at the sun's south pole, they did not find the tidy, orderly magnetic pole that everyone had assumed was there. They found something startlingly different. They found a mess. The map was wrong, and the reality of the pole was far more chaotic than the clean picture we had carried for so long. Recall the map we had drawn. We had imagined the sun's pole as a clean magnetic pole, much like the end of a bar magnet, with a single, well-defined magnetic polarity. Just as a bar magnet has a distinct north pole and a distinct south pole, we had pictured the sun's south pole as a clean region of a single magnetic polarity, orderly and simple. That was the tidy picture in our textbooks, the assumed reality of a place we had never seen. But when the spacecraft's magnetic mapping instrument actually measured the field at the South Pole, it revealed something quite different. Instead of a clean, single polarity, the instrument found both magnetic polarities present at the same time, jumbled together across the pole. Where we had expected one clean magnetic polarity, the instrument found a chaotic patchwork, with patches of one polarity and patches of the opposite polarity scattered across the polar region, all mixed up together. The scientists described it plainly. At the South Pole, the sun's magnetic field was currently a mess. Picture the difference. The map we had drawn showed a pole like the clean end of a bar magnet, a single, uniform magnetic polarity. But the reality the spacecraft revealed was more like a jumbled quilt, with patches of opposite magnetic polarities scattered across the pole, north polarity here, south polarity there, all tangled together in a chaotic mixture. It was not the orderly, single polarity pole we had imagined. It was a disorderly patchwork, a mess of mixed magnetic polarities, utterly unlike the tidy picture in our textbooks. When scientists looked at the magnetic map of the pole with its scattered patches of opposite polarities, they were seeing something that overturned the simple assumption we had carried. The pole of the sun was not a clean magnetic pole. It was a chaotic jumble. This was the great revelation, the reason this discovery mattered so much. We had drawn a map of the sun's pole based on assumption and inference, a tidy map of a clean magnetic pole. And when we finally saw the real thing, the map turned out to be wrong. The reality was messier, more chaotic, more surprising than we had imagined. This is the risk you always run when you map a place you have never seen, and here it had come true in the most striking way. The pole of the sun, that region we thought we understood, revealed itself to be far stranger than our simple picture had suggested. But now, an important and honest question arises. Was this mess a complete shock to scientists? Did it overturn everything they thought they knew? Here, the story takes a twist that is crucial to understand, because the truth is more subtle and more interesting than simply saying the scientists were blindsided. In fact, in one important sense, this mess was exactly what the deeper theories had predicted. Before we get to that twist, let's make sure we really understand what the spacecraft found, because it is genuinely strange, and it is worth picturing clearly. At the sun's south pole, the magnetic mapping instrument found both north and south magnetic polarities present at the same time. Now, if you stop and think about it, that is a deeply bizarre thing to say about a pole. It is worth unpacking exactly why. Consider an ordinary magnet again, because it is the clearest point of comparison. A simple bar magnet has two ends, and each end is a single, pure magnetic polarity. One end is entirely a north magnetic pole. The other end is entirely a south magnetic pole. You do not find patches of north polarity mixed into the south end of the magnet. The poles are clean and distinct, each one a single polarity. This is what we mean by a well-behaved magnetic pole, and it is the picture we had applied to the sun. We expected the sun's south pole to be like the south end of a bar magnet, a clean region of a single magnetic polarity. But that is not what the spacecraft found. At the sun's south pole, it found both polarities at once, patches of north polarity and patches of south polarity, scattered together across the same region. It was as if the south end of a bar magnet had somehow become a jumble of both north and south, a mixture where there should have been a single, pure polarity. This is what made the finding so striking. The very concept of a pole implies a single, dominant polarity. That is what a pole is. And yet the sun's south pole, when finally seen, did not have a single dominant polarity at all. It had both, mixed together in a chaotic patchwork. The magnetic field at the pole was not settled and orderly, pointing consistently one way, but scrambled, with opposite polarities interleaved across the region. This is a fundamentally different picture from the clean, tidy pole we had drawn. It suggests a pole in a state of confusion, of transition, of turmoil, rather than a pole in a state of clean, settled order. The word the scientists used, a mess, really is the most accurate description. The magnetic field at the sun's south pole was in a genuine state of magnetic chaos, both polarities jumbled together where we had expected one. So the reality of the pole, as revealed by the spacecraft, was a place of magnetic turmoil, a jumble of mixed polarities utterly unlike the clean magnetic pole of our old map. This is what it means to say the map was wrong. We had pictured order and we found chaos. We had pictured a single polarity and we found both at once. The pole of the sun turned out to be a far messier, more turbulent place than our simple assumptions had suggested. And yet, as I hinted, this chaos was not a complete surprise to the scientists who study the sun most deeply. Because while the simple, textbook picture of a clean pole was indeed wrong, the more sophisticated theories of how the sun works had actually anticipated that the pole might look like a mess, at least at this particular moment in the sun's cycle. To understand this crucial twist, and to understand why the pole is in such turmoil right now, we have to turn to the great rhythm of the sun, and to a dramatic event that is happening at the sun's poles as we speak. To understand why the sun's pole is currently such a mess, we have to understand what is happening to the sun's magnetic field right now, at this very moment in its cycle. Because the chaotic, mixed polarity state of the pole is not a permanent feature. It is a snapshot of a dramatic event in progress, one of the most extraordinary things the sun does. Right now, the sun's entire magnetic field is in the process of flipping upside down. And the mess at the pole is the visible sign of that flip underway. Here is what is happening. The sun goes through its roughly 11-year cycle of activity, and at the peak of that cycle, at solar maximum, something remarkable occurs. The sun's magnetic field reverses. The north magnetic pole and the south magnetic pole swap places. What was the north magnetic pole becomes the south, and what was the south becomes the north. The entire global magnetic field of the sun turns over, flipping its polarity completely. This is a regular part of the solar cycle, happening once every cycle, at the time of maximum activity. And crucially, the sun is right now at or near this period of maximum activity, which means its magnetic field is in the middle of this great reversal. The flip is happening now. The sun's magnetic poles are in the process of swapping, the global field turning over as we watch. And this is exactly why the pole looks like a mess. During the flip, the pole is in a state of transition, of upheaval. The old magnetic polarity that used to dominate the pole is breaking down, weakening and fragmenting, and the new polarity that will eventually take over has not yet fully established itself. So during this transitional period, the pole is caught in between, with remnants of the old polarity and patches of the emerging new polarity all present at once, jumbled together. This is the mess the spacecraft saw. It is a pole caught in the middle of flipping, neither its old clean state nor its new clean state, but a chaotic in-between, with both polarities scattered across it. The mess is the signature of a pole in transition, a magnetic pole in the very act of reversing. And here is the important part. This messy, mixed polarity state is only temporary. It happens only for a short time during each solar cycle, at solar maximum when the field is flipping. After the flip completes, a single new polarity will slowly build up at the pole and take over, and the pole will return to a clean, orderly state. In several years, when the sun reaches the quiet part of its cycle, its solar minimum, the magnetic field will be at its most orderly, and the poles will once again be clean, single polarity regions. So the mess we see now is not the pole's permanent condition. It is a passing phase, a snapshot of a rare and dramatic moment, the moment of the great magnetic flip. We happen to catch the pole in the middle of turning over, in a state of temporary chaos. And this timing is crucial because it leads directly to the twist I mentioned, the reason the mess, while it overturned the simple textbook picture, was not actually a surprise to the scientists who understand the sun most deeply. Because they had predicted, based on their models, that at this moment in the cycle, the pole should look like exactly this kind of mess. Now we come to the twist that makes this story richer and more honest than a simple tale of a shocking discovery. Because when we say the map was wrong, we have to be careful and precise about exactly what that means. The simple, textbook picture of a clean magnetic pole was indeed overturned. But the deeper, more sophisticated understanding of the sun, the detailed theories that scientists use to model how the sun works, had actually predicted that the pole would look like a mess at this moment. In an important sense, the chaos confirmed the theories, rather than overturning them. Here is what happened. While the simple, popular picture of the sun's pole was that of a clean magnetic pole, the scientists who build detailed models of the sun's magnetic behavior had a more nuanced expectation. Their models of how the sun's magnetic field evolves through its cycle predicted that, at solar maximum, during the Great Flip, the pole should become a tangled mess of mixed polarities, with patches of north and south scattered all over the place. This was what the sophisticated theory predicted for this particular moment in the cycle. And when the spacecraft actually looked at the pole and found precisely this kind of tangled mess, the scientists' reaction was not shock, but a kind of satisfaction. One of the mission scientists put it clearly, saying that the models predicted a tangled mess of different patches of north and south polarity all over the place, and that this was exactly what they saw. In other words, the observation matched the detailed prediction. The mess was not a violation of the theory. It was a confirmation of it. This is a crucial point, and it is important to be honest about it because it reveals how science actually works. The discovery of the messy pole was not a case of scientists being completely blindsided, their understanding shattered. Rather, it was a case of finally being able to directly confirm what the best theories had predicted. The detailed models of the sun had anticipated that the pole would be messy at solar maximum, and the first direct observation of the pole verified that prediction. So, in a sense, the poles are not entirely mysterious realms after all. Their messy state accords with what the sophisticated theories expected. The scientists who understand the sun most deeply were, in this respect, proven right. The map that was wrong was the simple, naive one, the tidy textbook picture. The deeper, more detailed map drawn by the models was actually vindicated. So does this mean the discovery was not important, that it told us nothing new? Not at all. It was still a landmark achievement, and it still profoundly advanced our understanding, for reasons we will explore. But it is important to hold both truths at once. The simple picture of a clean pole was wrong, overturned by the messy reality. And yet the sophisticated models had predicted that messy reality and were confirmed by it. This is the twist, the nuance that makes the story more interesting than a simple tale of a shattered assumption. The real significance of the discovery lies not in overturning our theories, but in something else, something we need to understand clearly. Because even though the mess was predicted, the value of finally seeing the pole was enormous, and it lies in the difference between guessing and knowing. So let's be precise about what exactly was wrong with our old map, and why finally seeing the pole mattered so much despite the mess being predicted. Let's resolve the apparent tension in our story, because it holds the deepest lesson of all. If the sophisticated models had predicted the messy pole, then in what sense was our map really wrong? And why did finally seeing the pole matter so much, if it largely confirmed what the theories already expected? The answer reveals the true value of direct observation and the profound difference between guessing and knowing. Here is what was actually wrong with our old map. It was not that our best theories were badly mistaken. It was two other things, both important. First, the simple, popular textbook picture, the one that most people carried, the tidy image of the sun as a clean bar magnet with orderly poles at all times, was indeed wrong, or at least badly incomplete. That simple picture failed to capture the reality that the pole becomes a chaotic mess during the Great Flip at solar maximum. So the naive map was genuinely misleading, and finally seeing the pole corrected it. But the second, deeper sense in which our map was wrong is the most important of all. It was wrong because it was never actually verified. For the entire history of solar science, our picture of the pole, whether the simple textbook version or the sophisticated model version, was based on inference, extrapolation, and theory, never on direct observation. We had never actually seen the pole to check whether any of our maps were right. We were, in the deepest sense, mapping blind, filling in the pole with our best guesses without ever being able to confirm them. And this is why finally seeing the pole mattered so enormously, even though the mess was predicted. Because there is a profound difference between predicting something and actually confirming it by direct observation. Before the spacecraft looked at the pole, our models predicted a messy field, but that was just a prediction, an educated guess based on theory. We could not be sure the models were right, because we had never checked them against the real pole. When the spacecraft finally looked and found the predicted mess, it transformed that guess into knowledge. It converted an untested prediction into a confirmed observation. This is one of the most important things science can do, to take a theoretical prediction and verify it against reality, to move from thinking we know to actually knowing. The value of seeing the pole was not that it overturned our theories, but that it finally allowed us to test them, to confirm them, to replace inference with direct evidence. We had been drawing maps of a place we had never seen, and now, for the first time, we could check those maps against the real territory. So the true story is this. Our simple map was wrong, and even our sophisticated map was unverified guesswork. And the achievement of finally seeing the pole was to replace all of that guesswork with real observation, to confirm what the best theories predicted while correcting the naive picture, and to open the door to discovering things we could not have predicted at all. Because here is the exciting part. While the general messiness of the pole was predicted, the detailed, direct observation of the pole also revealed specific things that the models had not gotten right, surprises hidden in the details that only direct observation could uncover. The spacecraft did not just confirm the mess. It found genuine surprises about how the pole behaves, surprises that are already forcing scientists to revise their models. And the first of these surprises concerns a great river of plasma that flows across the surface of the Sun, a conveyor belt that carries the magnetic field toward the poles, and that turns out to move in ways we did not expect. To understand the genuine surprises that the spacecraft uncovered at the pole, we first need to understand one of the most important and beautiful features of the Sun, a vast circulation of plasma that flows across its surface and through its interior, carrying the magnetic field along with it. This great circulation is often described as a conveyor belt, and it plays a central role in driving the Sun's magnetic cycle and in building up the very polar fields we have been discussing. Here is how this conveyor belt works. The Sun is a churning ball of plasma, and within it, there are large-scale flows of material, great currents of plasma moving in organized patterns. One of the most important of these is a circulation that runs between the Sun's equator and its poles. Near the surface of the Sun, plasma flows from the equator toward the poles, streaming across the surface from the middle of the Sun up toward the top and bottom. Then, deep in the Sun's interior, the plasma flows back the other way, returning from the poles toward the equator, completing a great circulating loop. This is like an enormous conveyor belt, carrying plasma from the equator to the poles along the surface, and back from the poles to the equator through the interior. There is one of these great circulations in each half of the Sun, one in the northern hemisphere and one in the southern, each carrying plasma in this looping conveyor belt pattern. And these circulations are thought to set the pace of the Sun's 11-year cycle, governing the rhythm of solar activity. Crucially, this conveyor belt carries the Sun's magnetic field along with it. Because the plasma is electrically charged, It drags the magnetic field with it as it flows. So as the plasma streams from the equator toward the poles along the surface, it carries magnetic field with it, transporting magnetic field up toward the poles. This is a key part of how the polar magnetic field gets built up. The conveyor belt carries magnetic field from the lower latitudes up to the poles, depositing it there, gradually building up the polar field over time. So the strength of the polar field, that crucial seed for the next cycle, depends in part on how this conveyor belt operates, on how it carries magnetic field up to the poles. Understanding this conveyor belt is therefore central to understanding the sun's magnetic cycle and to predicting how strong future cycles will be. It is one of the key mechanisms driving the entire rhythm of solar activity. And here is where the spacecraft's view of the pole became so valuable. For the first time, by looking down on the pole from above, the spacecraft could observe this conveyor belt in action at high latitudes, near the pole itself, where it deposits its magnetic field. It could measure how the plasma and the magnetic field were flowing toward the pole, tracking the operation of the conveyor belt in a region we had never been able to observe directly before. This was a chance to see, for the first time, how the magnetic field was actually being carried up to the pole, to watch the conveyor belt at work in the very region where it matters most. And when scientists made these measurements, when they tracked how the magnetic field was flowing toward the pole, they found a surprise. The conveyor belt was carrying the magnetic field toward the pole faster than they had expected. And this unexpected speed is a genuine new finding, one that direct observation revealed, and that is already prompting scientists to reconsider their models. Here is one of the genuine surprises that direct observation of the pole uncovered, a finding that the models had not gotten right, and that only seeing the pole could reveal. When scientists used the spacecraft to measure how the sun's magnetic field was being carried toward the South Pole by the great conveyor belt of plasma, they found that it was moving faster than expected. The magnetic field was migrating toward the pole more quickly than the models had predicted. And this unexpected speed is a real, new piece of knowledge, the kind of surprise that can only come from actually observing a thing rather than modeling it from afar. Let's understand what was measured. Using its instruments, the spacecraft was able to track the flows of plasma and the migration of the magnetic field at high latitudes near the South Pole. It measured the speed at which the magnetic field was drifting toward the pole, carried along by the conveyor belt of plasma flowing across the surface. And the measured speed, while modest in absolute terms, a gentle drift of the magnetic field poleward, turned out to be faster than scientists had anticipated based on their models. The magnetic field was being transported toward the pole more quickly than expected, migrating poleward at a rate that surprised the researchers. This might sound like a small detail, but it is genuinely significant because the speed at which magnetic field is carried to the poles affects how the polar field builds up, and therefore affects the whole magnetic cycle and our ability to predict it. This is exactly the kind of finding that demonstrates the value of finally seeing the pole directly. Remember, the general messiness of the pole had been predicted by the models, but this specific detail, the unexpectedly fast migration of the magnetic field toward the pole, was a genuine surprise, something the models had not correctly anticipated. It is a discovery that could only be made by directly observing the pole, by actually measuring the flows and the field migration in that region. No amount of theorizing from afar could have revealed this. It took direct observation, the first ever direct view of the pole, to uncover this unexpected behavior. And now that scientists know the magnetic field moves toward the pole faster than they thought, they can revise their models, improving their understanding of how the polar field builds up and how the solar cycle works. This is science advancing through direct observation, correcting and refining our models with real data from a region we had never seen. So even though the messy poll confirmed the general predictions, the direct observation also revealed genuine surprises in the details, like this unexpectedly fast migration of the magnetic field. This is the true payoff of finally seeing the pole. It is not just about confirming what we suspected. It is about discovering the things we did not suspect, the details that only direct observation can reveal, and using them to refine our understanding of the sun. And this fast migration is just one of the surprises, because the spacecraft's measurements of the polar field also revealed something potentially important about the strength of that field, something that may have implications for the sun's behavior in the years to come. The polar field, it turns out, may be unusually weak right now, and that weakness could be a clue about how quiet or how active the sun's next cycle will be. As scientists studied the magnetic field at the sun's poles with the help of the spacecraft's unprecedented measurements, another intriguing finding emerged, one that reaches beyond the mess of the current flip and hints at the sun's future behavior. The magnetic field that is building up at the poles, the field that will eventually take over once the flip completes, appears to be unusually weak. Compared to recent cycles, the polar field looks faint, and this potential weakness could be a significant clue about what the sun will do in the years ahead. To understand why this matters, recall the crucial role of the polar field. After the great magnetic flip completes, a single new polarity slowly builds up at each pole, and the strength of that new polar field is one of the best predictors we have of how strong the sun's next cycle of activity will be. A strong polar field tends to be followed by a strong, active next cycle, with many sunspots and frequent eruptions. A weak polar field tends to be followed by a weaker, quieter next cycle, with less activity. So the strength of the polar field as it builds up is like an early forecast of the coming cycle, a hint of whether the next round of solar activity will be intense or mild. And this is why the apparent weakness of the current polar field is so intriguing. If the polar field building up now is unusually weak, it could mean that the sun's next cycle of activity will be unusually quiet, with fewer sunspots and fewer eruptions than in recent cycles. Indeed, when scientists assessed the strength of the sun's polar field, they found indications that it is at an unusually weak level compared to the last several solar cycles. This is a genuinely interesting finding, because it suggests that the coming solar cycle might be on the weaker side, potentially one of the quieter cycles in recent history. Of course, there is uncertainty here. The polar field could still strengthen in the coming years before the next cycle begins, and predicting the sun's behavior is notoriously difficult. But the current indication of an unusually weak polar field is a real clue, a hint that the sun may be heading toward a quieter phase. And it is exactly the kind of insight that improved observations of the poles can provide. By measuring the polar field directly and accurately, the spacecraft is helping scientists refine their forecasts of the sun's future activity, offering an early glimpse of what the coming cycle might hold. This finding highlights, once again, why seeing the poles matters so much. The polar field is a key to predicting the sun's future, and the better we can measure it, the better we can forecast the solar activity that affects the Earth. The spacecraft's ability to observe the poles directly, from its unique vantage point above the ecliptic, is already improving our measurements of the polar field, and therefore our ability to predict the sun's behavior. The vanishing field, the unusually weak polar field building up now, is both a scientific curiosity and a practical clue, a hint about the sun's future that we could only obtain by finally seeing the poles clearly. And the surprises do not end there. Because the spacecraft's view of the pole also hinted at something even stranger, a possible feature at the pole of the sun that would echo something we have seen on other worlds, a great swirling vortex at the very top of our star. Among the intriguing possibilities that the spacecraft's view of the pole opened up, there is one that is especially tantalizing, a hint of something at the top of the sun that would echo a phenomenon we have seen on other worlds. As the spacecraft tracked the flows of material over the sun's pole, it raised the possibility that the pole might host a great swirling vortex, a rotating circulation of material at the very top of our star, similar to the polar vortices found on some of the planets. If confirmed, it would be another way in which the pole of the sun is stranger and more dynamic than we ever knew. To understand this possibility, think about what we have seen at the poles of other worlds. Several of the planets in our solar system have remarkable features at their poles: great swirling storms and vortices, circulations of atmosphere rotating around the polar point. One of the giant planets, in particular, is famous for the striking vortices at its poles, including an extraordinary swirling structure that has fascinated scientists. These polar vortices are dramatic features, great rotating systems centered on the pole, driven by the planet's rotation and the flows of its atmosphere. And now, with the first views of the sun's pole, scientists have begun to wonder whether the sun, too, might have such a feature at its poles. Could there be a great vortex at the top of the sun, a swirling circulation of plasma rotating around the polar point, echoing the vortices we see on the planets? The spacecraft's ability to track the flows of material over the pole is exactly what is needed to investigate this possibility. By measuring how the hot gas is moving across the polar region, scientists can look for signs of a rotating, swirling circulation, a vortex centered on the pole. The early observations hinted that such flows and circulations might be present, raising the exciting possibility that the sun has polar vortices similar to those on the planets. This is not yet a settled conclusion. It is an emerging possibility, a hint that future observations will need to confirm or refute. But the very fact that we can now investigate it, that we can look at the flows over the sun's pole and search for a vortex, is a testament to how much this first view has opened up. A question we could never even properly ask before, whether the sun has polar vortices, is now something we can actually investigate, thanks to the first direct views of the pole. If the sun does turn out to have great vortices at its poles, it would be yet another way in which the pole is a rich, dynamic, surprising place, far more complex than the simple, tidy region of our old map. It would mean that the top of the sun has its own swirling weather, its own rotating circulations, echoing the dramatic polar features of the planets. And it would deepen the picture of the pole as a region of genuine complexity and activity, full of flows and fields and possibly vortices, a place we are only just beginning to understand. This possibility of a polar vortex is one more example of how finally seeing the pole has transformed it from a blank spot on our map into a rich frontier of discovery, full of surprises we are only starting to uncover. And all of these discoveries, the messy field, the fast migration, the weak polar field, the possible vortex, matter not just for their own sake, but because of what the pole ultimately controls. Because hidden in the pole of the sun is the seed of the future, the key to predicting the sun's behavior in the years to come, and therefore the key to protecting ourselves from the sun's most dangerous moods. Let's bring all of these discoveries together and understand why they matter so much, not just to scientists, but to every one of us here on Earth. Because the pole of the sun, that region we had never seen until now, holds within it the seed of the sun's future. The magnetic field at the pole is one of the best predictors we have of the sun's next cycle of activity, and that cycle determines the space weather that reaches the Earth, the storms that can threaten our technology and our way of life. In finally seeing the pole, we are getting closer to being able to predict the sun, and that has real consequences for all of us. Here is the chain of connections that makes the pole so important. The magnetic field at the pole builds up over the course of the solar cycle, and its strength, when the sun is quiet, forecasts how strong the next cycle of activity will be. That next cycle determines how many sunspots the sun will have, how many flares it will unleash, how many great clouds of charged particles it will hurl out into space. And those flares and clouds, when they are aimed at the Earth, create the space weather that can disrupt our satellites, damage our power grids, interfere with our communications and navigation, and endanger astronauts. So there is a direct line from the magnetic field at the sun's pole to the space weather that affects our daily lives. The pole is, in a very real sense, the source of our ability to forecast the sun, the region that holds the clues to the sun's future behavior, and therefore to the space weather headed our way. This is why finally seeing the pole is not just a scientific curiosity, but a genuinely practical achievement. The better we can observe and measure the polar magnetic field, the better we can predict the sun's next cycle, and the better we can prepare for the space weather it will bring. Being able to forecast the sun's activity means being able to anticipate the dangerous solar storms that could damage our technology, giving us time to prepare and protect our vital systems. In an age when our civilization depends so heavily on satellites, power grids, and electronic communication, the ability to forecast the sun's behavior is enormously valuable. And that ability depends, in large part, on understanding the poles, on measuring the polar magnetic field that seeds the next cycle. By finally seeing the pole, we are taking a crucial step toward better forecasts of the sun, and therefore toward better protecting ourselves from its most dangerous moods. So the discovery of the messy pole and all the findings that came with it matter far beyond the realm of pure science. They are steps towards solving a practical problem that affects us all, the problem of predicting the sun. The pole holds the seed of the next cycle, and understanding it brings us closer to forecasting the solar storms that threaten our technological world. This is the ultimate payoff of finally seeing the last unseen place, the reason it was worth the years of effort and the long climb out of the ecliptic plane. And yet, for all this progress, there remains a humbling truth at the heart of it all. Because even now, even with our first views of the pole, even with all our models and measurements, there is one thing about the sun that we still cannot reliably do. We still cannot fully predict it. The deepest mystery, in the end, remains unsolved. For all the triumph of finally seeing the sun's pole, for all the discoveries it has yielded, we must end our exploration with a dose of humility. Because there is a profound and somewhat surprising truth that remains, even after this historic achievement. Despite finally seeing the pole, despite all our sophisticated models, despite decades of studying the sun in extraordinary detail, we still cannot reliably predict the sun's behavior. The deepest mystery, the one that motivated so much of this effort, remains stubbornly unsolved. We still cannot say, with confidence, exactly when the sun's magnetic field will flip, or precisely how strong its next cycle will be. This is genuinely remarkable when you think about it. The sun is our nearest star, the most thoroughly studied star in the universe, watched continuously for decades, probed by a fleet of spacecraft, modeled by some of the most sophisticated theories in all of science. And yet, we still cannot fully predict its great cycle of activity. Current models struggle to forecast exactly when the magnetic field will reverse and struggle to predict the strength of the coming cycle with real precision. The sun's behavior remains, in important ways, unpredictable, defying our best efforts to forecast it. This is not for lack of trying, and not for lack of data. It is because the sun is an extraordinarily complex system, its magnetic field generated by intricate flows of plasma deep within it, governed by processes that we do not yet fully understand. The great cycle of solar activity emerges from this complexity, and capturing it well enough to make reliable predictions has proven to be one of the great challenges of solar science. And this is precisely why seeing the pole matters, and also why it is not, by itself, a complete solution. Seeing the pole gives us crucial new information, a direct view of the region that seeds the next cycle, better measurements of the polar field that forecasts solar activity. It is a major step toward better predictions, but it is not a magic key that suddenly makes the sun fully predictable. The sun remains a complex, challenging system, and even with our first views of the pole, much about its behavior remains mysterious. What seeing the pole does is give us a vital new tool, a new source of data that can help improve our models and our forecasts over time. It moves us closer to predicting the sun without completing the journey. The prediction we still cannot reliably make, the forecast of the sun's future activity, remains a work in progress, an ongoing challenge that the new views of the pole will help us tackle, but have not yet solved. There is something fitting and even beautiful about this. It reminds us that even our nearest star, even the object we have studied more than any other, still holds deep mysteries, still humbles us with its complexity. We have finally seen the pole, filled in the last great blank spot on our map, and yet the sun continues to keep some of its secrets. This is the nature of science, and of the sun. Every answer reveals new questions. Every discovery opens new frontiers. Finally seeing the pole has taught us a great deal, confirmed some of our theories, corrected others, and revealed genuine surprises. But it has also reminded us how much we still have to learn about our own star. And the good news is that the effort to learn is far from over, because the spacecraft that gave us our first view of the pole is still climbing, still rising higher above the ecliptic plane, and in the years to come, it will give us even better views, allowing us to redraw the map of the pole in ever greater detail. Our story does not end with the first images of the pole. In fact, in a very real sense, it is only beginning, because the spacecraft that captured those first historic views is still on its mission, still climbing its stairway out of the ecliptic plane, and in the years ahead, it will rise higher and higher above the level of the sun's equator, obtaining ever better, ever clearer views of the poles. The first images were just the start. The map of the pole, drawn wrong for so long and finally corrected, is now being redrawn in ever greater detail, a living map that will grow richer with each passing year. Remember how the spacecraft reached its vantage point, by using the gravity of a planet to gradually tilt its orbit higher and higher above the ecliptic plane. That process is not finished. The spacecraft will continue to make flybys of the planet, and each one will lift its orbit further, tilting it to steeper and steeper angles above the sun's equator. So in the coming years, the spacecraft will climb even higher above the level of the equator, gaining an even better view of the poles than it had for those first images. From these higher vantage points, it will be able to look down on the poles more directly, seeing them more clearly, measuring their magnetic fields and flows with greater precision. The views we have seen so far, remarkable as they are, were captured from a relatively modest angle above the equator. As the spacecraft climbs higher, its views of the poles will improve dramatically, revealing the polar regions in unprecedented detail. The best views of the pole are yet to come, and this means that our understanding of the pole will keep growing, keep deepening in the years ahead. Each new campaign of observations from each higher vantage point will add to our picture of the pole, refining our maps, correcting our models, and revealing new surprises. We will watch the pole as the great magnetic flip completes and the new polarity builds up. We will track the conveyor belt of plasma more precisely. We will search for polar vortices and measure the polar field with ever greater accuracy. We will see how the pole changes through the solar cycle, building up a dynamic picture of this region as it evolves over the years. The mission scientists have made clear that these first views are only the beginning, that the data to come will transform our understanding of the sun's magnetic field, its wind, and its activity. We are at the dawn of a new era of solar exploration, an era in which the poles of the sun, hidden for all of history, are finally open to our view. So the map of the pole, wrong for so long and only now being corrected, is a living, growing thing, being redrawn in ever greater detail as the spacecraft climbs higher and sees more. We have taken the first step, filled in the blank spot with a first true image, and discovered that the reality is messier and more surprising than we imagined. And now, the work of mapping the pole properly, of understanding it fully, is underway and will continue for years to come. The last unseen place has been seen, and now it will be explored, mapped, and understood as never before. This is the ongoing adventure of solar science, the patient, thrilling work of replacing our old guesses with real knowledge, of drawing, at last, a true map of the top of our own star. And it all began with a single, historic first look, the moment we finally saw the pole and discovered that the map was wrong. So the next time you feel the warmth of the sun on your face, take a moment to consider something remarkable. For the entire history of our species, until just recently, we had never seen the top of that star. We knew the sun intimately in so many ways, watched it every day, studied its light and its storms and its spots. And yet its poles, the very top and bottom of our nearest star, remained hidden from us, an unexplored frontier at the heart of our own solar system. It is a humbling thought that something so close, so familiar, so essential to our lives, could hold a region we had never once laid eyes on. We began tonight with a map that was wrong, a tidy, orderly picture of the sun's pole drawn from assumption and inference, never verified by direct observation. We imagined a clean magnetic pole, simple and well-behaved, like the end of a bar magnet. And then, at last, a spacecraft climbed high enough to look down on the pole for the first time and showed us the truth. The real pole was not tidy and orderly. It was a mess, a chaotic patchwork of mixed magnetic polarities, a pole caught in the middle of a great magnetic flip. The simple map we had carried was wrong, corrected at last by the first true view. And though the deeper theories had anticipated the mess, the value of finally seeing it was immense, transforming our guesses into knowledge and revealing genuine surprises hidden in the details, from the unexpectedly fast migration of the magnetic field to the possible swirling vortices at the very top of the sun. There is a profound lesson in all of this, one that reaches beyond the sun itself. It is a lesson about the difference between assuming and seeing, between the maps we draw from our theories and the reality we discover when we finally look. For all of history, we had filled in the blank spot at the sun's pole with our best guesses, and we had grown comfortable with our tidy picture. But when we finally saw the real thing, we discovered it was stranger and messier than we had imagined. This is how knowledge advances, not by resting on our assumptions, but by pushing to see for ourselves, by climbing, however difficult it may be, to a vantage point from which we can finally observe the truth. The map was wrong, and only by looking did we learn how to make it right. And even now, with our first true views, the deepest mystery of the sun, the challenge of predicting its behavior, remains unsolved, a reminder of how much we still have to learn about our own star. So look up sometimes at that bright and familiar sun, and remember that at its very top, there is a region we have only just begun to see, a place that was hidden for all of history and is now, at last, coming into view. Remember that a spacecraft is up there right now, climbing higher and higher, redrawing the map of the pole in ever greater detail, revealing the last unseen place as never before. And remember the humbling truth at the heart of it all, that even our nearest star, the source of all life and warmth, still holds mysteries we are only beginning to unravel. The true map of the sun is still being drawn, one historic image at a time. We have seen the pole at last and found that the old map was wrong. And now, with open eyes and endless curiosity, we are drawing the true map of our star and discovering in the process just how much wonder remains to be found, even in the light that shines down on us every single day.